Hello everyone, I once again welcome you on to MSB lecture series on transition elements. Today let me discuss about the 18 electron rule and also effective atomic number. In my previous lecture I informed about ligand field theory's importance and how ligand field theory effectively explains bonding in coordination chemistry, and also it is capable of explaining almost all properties related to transition metal compounds and also organometallic compounds. Today let me introduce another important topic, that is the 80 electron rule, that means electron counting, and what are its significances, what we should follow while counting electron rule, what does it mean to coordination compounds or organometallic compounds stability and their application. All those things let us study in detail. I shall give you numerous examples so that you will become familiar in electron counting. First of all, let us try to look into what is 18 electron rule. It is a way of expressing the tendency of a transition metal atom to use all its valence shell. When we talk about transition elements, we have 3 valence orbitals, that is Nd orbitals and n plus 1 s orbital and n plus 1 p orbitals. That means we have a total of 5 plus 1 plus 3, 9 orbitals with a capacity of 2 electron each, means 18 electrons. So, these metals have a tendency to have as many electrons as possible into their valence shell, so that it will be having 18 electron at the end, and that is called 18 electron rule. Just recall about the octet rule we use in main group compounds, especially for p block elements, introduced by Gilbert and Lewis. What it says is we have p block elements having S2p1 to S2p6 electronic configuration. That means we start with 1 electron in the p orbital starting from boron group to end with 8 electrons in the valence shell along with S2 electrons, that is inert gases. That means most of these p block elements have a tendency to have as many as 8 electrons to have stability and attain next inert gas configuration. And if you just look into any ion, okay, whether it is a cation or anion, they always make an attempt to have next inert gas configuration. If it is not possible, they lose some electrons to become positively charged one to attain previous elements or previous gas inert gas configuration. For example, if you take N3 minus, it has S2p3 and another 3 will become S2p6, so that it becomes a next inert gas configuration. Similarly, oxygen with S2p4, it will take 2 more electrons to become O2 minus, and similarly if you go for chlorine, bromine, iodine or fluorine, they have 7 electrons, they need 1 electron, that is the reason they make monoanions. That means whenever you look into a stable cation or anion, it must satisfy inert gas configuration, whether the next one or the previous one. In the same way, if you extend the same octet rule to transition elements, here instead of having 4 orbitals with capacity of 8 electrons, we have 9 orbitals with a capacity of 18 electrons. As a result, we call it as 18 electron rule. The sum of the number of valence electrons in the gaseous atom plus the number of electrons from neutral or ionic ligands may attain a maximum value of 18. That means, is it really true that 80 electron rule must be obeyed by all transition elements? Before I answer that question, let us look into simple examples here. So, I have given here chromium hexacarbonyl. You know chromium electronic configuration, it is 3d4 4s2 or 3d5 4s1, does not matter. So, it has 6 electrons and plus 6 carbonyl groups are giving 12 electrons here. So, it becomes 18. So, it obeys 18 electron rule. Now, let us look into this one here, and in this one let us assume H is giving 1 electron. There are 2 methods to count electrons. One is called ionic method, other one is called neutral method or covalent method. In ionic method, we are defining the oxidation state of the metal depending upon how many anionic ligands are present. In the neutral or covalent method, we are ignoring and we are just counting all electrons from the metal and before its oxidation, and then we are giving 1 electron for chloride or 1 electron for hydrogen. So, it goes that way. In the next slide I will make you familiar with counting electrons, and to make you familiar with different ligands can give how many electrons from in both ionic method as well as in covalent method. So, now if you consider, let us consider here using neutral method. So, here we have 4d6 5s2. So, 8 electrons are there, and then this hydrogen is giving 1 electron, and then this acetate is giving 1 electron, and then this they are giving 6 electrons. It becomes 16 electrons, but in this acetate what happens, this also giving 2 electrons. As a result, you add another 2, it becomes 18 electron. So, now let us go for other method. So, now we know that oxidation of ruthenium is +2 here, because one is H minus, one is acetate Ca3COO minus. Therefore, here we have 6 electrons, and now H2 is a 2 electron donor and acetate is a 4 electron donor now, and plus 6. So, this is 18 electron. So, this is how you can count, and in this case it is very straightforward. Iron has 8 electrons, 3d6 4s2. So, we have 8 electrons, and then in this case carbon monoxide is 5 into 2 10, it is 18 electrons. So, whatever the complex I have shown here, all of them obey 18 electron rule. So, same thing I have shown here. Now, I will introduce another term called effective atomic number. This was introduced by Sidgwick. So, electron pairs from the ligands are added until the central atom is surrounded by the same number of electrons as the next noble gas. It is essentially same. What in 18 electron rule we did was we counted only valence electrons. If you count all the electrons including those coming from ligands in a metal complex, that is essentially called as effective atomic number EAN. Metals with odd number of electrons can never attain noble gas configuration. That means there are some exceptions. If the electrons are added in pairs, metals with odd number of electrons can never attain noble gas configuration. It is necessary to produce a symmetric structure irrespective of number of electrons involved. That means always when we do not know the structure, when we make an attempt, we should try to write a symmetric structure to a given complex. Now, I have given more examples here. Let us look into these examples to calculate the effective atomic number in each case. And you consider chromium here, atomic number is 24. Chromium, as I mentioned, electron lost during the formation of this one is 0, because 0 oxidation state, and electron gained is 12. So, what we have is here 24 plus 12, it is 36. So, it attains, this is the effective atomic number for chromium hexacarbonyl. Similarly, if you take iron, the first one here in this one. So, here iron is in +2 state, iron is +2 state, 2 electrons are lost here. So, we will be left with 24 electrons, and then 6 cyanates are giving 12 electrons, this is also 36. Okay. Now, if you take this one, so electron lost are 3 here. So, we will be left with 25, and now 12 electrons are coming here, then it would be 35. So, 1 electron less than next inert gas atomic number. Let us look into iron pentacarbonyl. Here electrons lost are 0, and then 10 electrons are coming, 26 plus 36. Yes, this also attains effective atomic number. Now, if you look into copper, so 1 electron is lost here, copper is in +1 state, and then ligands are donating 8 electrons. So, it becomes 36. So, it follows. Nickel, if you consider, nickel has 8 electrons, 2 electrons are lost and 12 electrons are coming. So, that means 26 plus 38, it does not obey, we have 2 electrons excess. Okay. So, next same thing is true in this case also. Instead of 6 ammonia, we have 2 ammonia and 2 bidentate ligands ethylene diamine. The total number of electrons coming are again 12. So, here again 38. It does not obey. And if you consider this compound here, the electron lost are because Cp cyclopentadienyl anion, 1 electron is going from ruthenium, 1 electron is going from towards chloride. So, we have ruthenium is having 6 electrons, and now what we have is this is 6 electrons are there, 6 plus 8, 10 and 12, 54 we have. So, this satisfies effective atomic number. This is how you can calculate the, I have shown here, we can verify whether it is correct or not. Yes. So, this is how you can count the electrons, and also you can write the effective atomic number, and also you will be knowing whether a given complex satisfies 18 electron rule or not. Now, the question is, why some metal complexes can never obey 18 electron rule? Is it true? If you look into 3D metals can have a maximum coordination number of 6 with an octahedral geometry. So, that means 12 electrons are guaranteed when it forms an octahedral complex with coordination number 6. Then if 12 electrons are coming from ligands, metal should possess at least 6 electrons in order to satisfy 18 electron rule, but by virtue of being a early metal does not have more than 6 electrons in their d orbital, then it can never obey 18 electron rule despite having coordination number 6 and 6 ligands surrounding it. That means the metals having an electronic configuration of D1, D2, D3, D4 and D5 with monometallic complex formation, even with coordination number 6, they can never obey 18 electron rule, because we will be having less electrons within the metal itself prior to the complex formation. And again, metals with odd atomic number can never obey 18 electron rule. On the other hand, if metals have more than 6 electrons with coordination number 6, they also do not obey 18 electron rule, because they will be having excess electrons that we saw in case of hexamine nickel 2+ complex. That means outer orbital complexes always have slightly excess electrons than the next inert gas. As a result, they are unstable and they do not obey 18 electron rule. So, now again to make you familiar with electron counting, I am just showing you here 3 different type of ligands we come across. One is 2 electron donors, and here in the neutral method they are all 1 electron donors, and here of course this does not come into picture. Here we have Lewis acids, and of course in case if you come across, then you have to subtract 2 electrons for Lewis acids if they are present on a metal center while electron counting. So, now I shall make you familiar with the different ligands we come across and how many electrons they will contribute when in ionic method and covalent method. H, what happens, it has 1 electron. So, covalent method it is a 1 electron contributor, but when you take 1 electron from the metal oxidation state increases by +1, and hence that electron will come and it becomes H minus. Now, we have 2 electrons, so it becomes 2 electron donor. In the same way, if you take halides, they are all 1 electron donor in covalent method, but they are 2 electron donor in ionic method, because they have this pair of electrons that can go to the metal. Same thing is true in case of hydroxide, cyanide and also methyl. So, in all these cases covalent method always you consider 1 electron. When you are using ionic method you consider 2 electrons, and this extra electron you should remember that is coming from the metal. Accordingly, metal oxidation state increases and number of d electrons decreases. In case of NO, if it is bent, it is a 1 electron donor, but in ionic method it is also 2 electron donor. And carbon monoxide and tertiary phosphines, they are, whether you consider ionic method or covalent method, they are 2 electron donors. And then this is ethylene, olefins, they are 2 electron donors both in ionic method and covalent method. And with all neutral ligands, if you consider, they are irrespective of method A or method B, they are always 2 electron donors. So, if you consider this pi bonding, then they are 2 electron donor. If you consider oxide O2 minus, then they are 2 electron donors or they are 4 electron donors. Similarly, if you consider NO with linear, they are 2 electron donor in method A and 3 electron donor in method B, and ethylene again 2 electron donor in ionic method, and covalent method they are 3 electron donor, and in ionic method they are actually 4 electron donors. In case of acetylene 3 minus, they are 3 electron donor here, and here it will be 6 electron donor. In ionic method they are 6 electron donor, whether here they are 3 electron donor, and butadiene 4 electrons or 4 electron donor. Cp minus, it is 6 electron donor, whether consider just Cp it is a 5 electron donor. Eta 6, a benzene for example, it is a 6 electron donor, here also 6 electron donor. And if you consider tropylium ion, it is a 6 electron donor cation, otherwise it is 7 electron donor. So, now you are familiar with assigning the electrons that are coming towards the metal from these ligands in both ionic method and covalent method. Now let us look into more examples. So, now I have given several examples here, that let us try to use both ionic method and covalent method. In case if you do not know the oxidation state, there is no need to worry. First let us make an attempt to write electron count using covalent method, and then if any anion is there, we will add one electron depending upon whether a monoion, dianion, trianion accordingly, and then count how many electrons are left on metal. You will end up with knowing the precise oxidation state of the metal center in that particular complex. And if you consider here, let us start with covalent method. Covalent method, this is 3d7 4s2. So, we have 9 electrons are there here, 9 electrons are there, and 2 CPs they are giving 10 electrons. So, this is becomes 19 electron species. Let us check now in ionic method. So, ionic method it is 7 electrons are coming, and Cp they are giving 12 electrons, because Cp minus will be 6 electrons. So, this is 17 electrons, later we can verify. And zirconium, this is 4d2 5s2. So, this is in plus 2 state here, whether it is plus 2 is 4 are there. So, it cannot be in plus 2 state, it has to be in plus 4 state, that is zirconium 4 state. So, in this case if you go for ionic method covalent method, we have 4 electrons here and 10 electrons are coming here, and 2 electrons are coming here. So, this is a 16 electron species, but if you go with ionic method, here 0 electrons are there and they are giving 12 electrons and they are giving 4 electrons to each. So, it becomes 16 electrons. So, it is matching. You see it is matching now. Now, if I add 2 electrons here and 2 electrons here, obviously you will be knowing the oxidation state of zirconium is plus 4. And now let us go to iridium. Iridium is cobalt, rhodium, iridium 5d7 6s2, and one chloride is there. So, let us not worry about that one. First let us write here 9 electrons and 1 electron is coming here, and then 6 electrons are coming from 3 triphenyl phosphine. So, 16 electrons are there, and similarly now we know the oxidation state, it is giving 8 electrons, and chloride is giving 2 electrons and 6 electrons. This is a 16 electron species. Though 16 electron species having D8 electronic configuration plays a prominent role in homogeneous catalysis for a variety of organic transformations. I shall tell you more details about the catalytic properties and how to use them in catalysis when I go to oxidative addition and additive elimination reactions at some point of this course. So, now let us look into molybdenum hexacarbonyl 0, that means 6 electrons are there and 12 electrons are coming here, 18 electrons, and same thing is true here, 6 plus 12 18 electrons. So, now I believe you are familiar with electron counting using both ionic method as well as neutral or covalent method. Let us look into it. So, 19, yes, prediction is correct, this is correct, and this is 16 electron species, and this is also 16 electron species. So, correct. So, tally works well. So, that now you know the oxidation state of zirconium is 4 here, it is not titanium, you correct it as zirconium. Of course, titanium, zirconium have similar properties when it comes to electron counting. Chemistry may be little different because one is 3D series, other one is 4D series. okay, 16 electrons, 16 electrons, 18, 18. So, electron count made simple. So, one should be able to use both ionic method and covalent method. What you should do is whenever you come across any metal complex, try to do electron counting to make yourself familiar with this process of electron counting. Now, CP binding, why we call it as eta 5, hapticity 5, I shall show you. So, we always make it like this C5H5, then where this 5 hapticity is coming for this one, let me write something like this. So, we are removing one electron, so we have a negative charge here and we have 2 bonds here. Now, first this one makes a bond to the metal through covalent bonding sharing electrons. Now, what happens, this is also a 2 electron donor, this can also go to the metal and this can also go to the metal, and then this one you can start writing resonance structure. This negative charge can keep on coming here, coming here, coming here, accordingly double bonds will be moving. As a result, what happens, it looks like delocalization occurs, and when delocalization occurs we write simply something like this, and negative charge, and we show here. So, that means here for this is for 2 electron eta 2, 2 electron eta 2, eta 4, and then 1 electron, and now this is considered as eta 5. So, this is how now one can explain bonding in case of CP having hapticity of 5. Now, I have 4 interesting dimeric species. By simple electron counting, you should be able to tell whether a metal-metal bond exists or not. If it exists, what is its nature, whether single bond is there, 2 bonds are there, or 3 bonds are there. Let us begin with a simple example of CO2 CO9. Of course, cobalt has 9 electrons in its valence shell, 9 means each one. So, 9 into 2 18, 18 is there, and another 18 electrons are coming from 9 carbon monoxide 18. So, 36 are there divided by 2. So, each cobalt has 18 electrons. So, it obeys 80 electron rule, and there is no need to include any metal-metal bond between 2 cobalt atoms. I will show you at the end its structure. So, it follows 18 electron rule. Now, let us look into the second one, cyclopentadienyl dicarbonyl dimer. So, here we know now iron is in +1 state. So, let us write directly here per iron I am writing. So, 6 electrons are coming, and then what we have is iron has 3 to 6 4s2, 1 electron is gone. So, we have 7 electrons, and then we have 4 carbon monoxides are there, and that means 2 carbon monoxide will contribute 4 electrons. So, we have 17 electrons are there, that means it is a 34 electron species, and if you do it is 17 electron, that means each iron cation has 17 electrons. In order to satisfy 18 electron rule, you have to establish a metal-metal bond, that means there will be one Fe-Fe bond will be there in it. Now, let us look into CO2 CO8. CO2 CO8, it is again 18 plus 16 electrons are there now. So, that means again 34 are there divided by 2, again you need a cobalt to cobalt single bond. Then look into the last case here. In this case what we have is again 6 electrons are there and 7 are there, but 1 carbon monoxide per, so 2 are there. So, that means 15 are there. So, 15 means you need 3 more electrons, so that probably there is a triple bond between 2 metal atoms. So, this is how you can predict, and also you should remember when you make an attempt to write the structure, you should try to make it as symmetric as possible. You can see here, yes, it is 80 electron, it does not need any. So, this is how the structure looks like. As I mentioned, you have to try to write symmetric structure. This is the only way you can write symmetric structure. Each cobalt has 3 terminal and 3 carbon monoxides are bridging. It is a very symmetric molecule and does not have any metal-metal bond. It does not need, because both of them have 80 electron each. Okay, now you consider this one. As I said, 1 electron is needed. Again, it is very symmetric and also it has centrosymmetry. So, you have to put a metal-metal bond, and you should remember, by adding a metal-metal bond, the number of electron does not become 36. you should remember remains 34 only. At a given time you can satisfy 18 electron rule for each one. When you are satisfying 18 electron rule for this one will be having only 16 electrons, you should remember, and when you are satisfying this one, this will be having 16 electrons. This is very similar to octet rule. Recall octet rule, when I wrote for carbon monoxide, I kept 6 electrons between 2 carbon monoxide and a pair of electron on carbon and oxygen. If you count simultaneously, you can never obey 18 electron rule, but on the other hand, when you count for oxygen, it has 8 electrons and carbon has only 4 electrons, but on the other hand, when you count for carbon, it has 8 electrons and oxygen has 2 electrons. So, this is how it is. So, you should remember that one. Simply by adding a metal-metal bond, you should not make it instead of 34 to 36, number of electrons remains same. Lot of students they do this kind of mistakes while counting electrons. You should not do it. Electrons are not coming from anywhere. Within, what we do is, in order to satisfy its octet rule, to make it stable, we are making a metal-metal bond. Now let us look into this example where we need one cobalt-cobalt bond, and that is the reason cobalt octacarbonyl, it undergoes dimerization. COCO4, if you make it, immediately dimerizes in order to satisfy 18 electron rule, and the structure looks like this. Of course, it can have both the structures and this is more stable, but one can also see this one, and of course you can analyze whether we have this structure or this one by just simply looking into IR spectroscopy, where carbon monoxide stretching frequency can precisely tell you whether you have this one or a mixture of both. So, here we have 30 electrons are there, we need 3 more bonds. So, this is how it is. For example, when I am counting electrons for this one, you should remember it has 80 electrons, but this will be having only 12 electrons, you should remember that one. Let me stop here and continue discussing 18 electron rule with more interesting molecules in my next lecture. Until then, keep calculating this 18 electron rule and try to make yourself familiar with it.